In this lecture, we're going to discuss ionic compounds, how ionic bonds are formed, and how that makes elements more stable than they were as an original atom. An ionic compound is a compound that is held together by ionic bonds. So this is a molecule that is made by more than one type of element, for example, sodium and chlorine, or aluminum and oxygen would be an ionic compound. An ionic bond is an electrostatic attraction that holds an anion and a cation, or more than one of each, together, almost like a magnet. And this results from the transfer of electrons between the atoms. As we talked about in our last lecture, electrons are either given away by one atom and they are going to be taken by the other atom. And the whole point of this is to have a full valence shell. That makes the atoms now more stable as ions, as part of the ionic compound in the molecule, than they were as atoms. This applies to all atoms except for the noble gases, which will never become ions. An example of an ionic bond is between sodium and chlorine to make the ionic compound sodium chloride, table salt. So in this example, we can see that the one valence electron on the sodium atom is going to be transferred or given away to chlorine to give chlorine a full outer shell. So this is a picture of what their Bohr models would look like as atoms. Once that electron has been transferred, we see that sodium now only has 2 energy levels, and its outermost energy level 2, is now a full outer shell, and chlorine now has a full 3rd energy level for full outer shell. So both of these atoms are now they have completed their valence shells, so they have a full octet. They fulfilled the octet rule. However, they now have these charges. Sodium is now a cation, and chlorine is an anion. So just like two magnets, they're going to be attracted to each other and stuck together now. A lot of times people think that bonding is when there's something that is connecting the two atoms, like there's a stick in between that attaches the two, and this isn't the case. It's just the magnetic pole is so strong, it's like a gravity between them, and it's strong enough that those two atoms are going to stick together no matter whether they are in the form of a solid, a liquid, or a gas, and they're going to stay together. So to form ionic compounds, you want to look at the electron configuration to figure out how electrons are going to be transferred. So for example, how many magnesium atoms and chlorine atoms are needed to make a neutral molecule of magnesium chloride? So if we look at magnesium, it has 2 valence electrons. We know from our last unit on ions, it's going to choose to lose those electrons, which makes it Mg2+ as a cation. Chlorine has 7 valence electrons. We know from our last unit that it's going to choose to gain 1 more electron to have a full outer shell, which leaves it as a Cl1- anion. The problem is that chlorine is only going to accept 1 electron to fulfill its octet rule. So 2 atoms of chlorine are needed in order to take both of these electrons from magnesium. So it's going to look something like this. Here's magnesium with its 2 valence electrons. 1 electron is transferred to 1 chlorine atom. The second electron is transferred to the other. And so now we have magnesium chloride. All 3 atoms now have a full outer shell. They've all fulfilled the octet rule, so they're all much more stable. And now they're going to be stuck together as an ionic compound because of their opposite charges. So the magnesium is going to be attracting both 1 chloride ion and the other. We can also figure out how many there are of each atom by looking at their charges, because the number of cations, or the total charge of the positiveness, must be equal to the total charge of all of the anions together, or the negative charge, to make an overall charge of 0. And if we counted out the number of protons and electrons available in the magnesium atom and the chlorine atoms, and then the chlorine ions after electrons are transferred, we find that all together as a group between all 3 atoms, the number of protons and electrons is equal, which is why it has an overall charge of 0. But we can also look at that as the charge of all of the cations together, which in this case is only 1, and all of the anions together. They even out to become a neutral charged molecule, or a net 0 charge. And that's due to the same reasons. So we can think of this mathematically by looking at 1 cation its charge is 2 plus. So overall, the whole cation charge component is 2 plus. We have 2 anions, each of them with a -1 charge. So overall, the whole anion component is a -2. So now we can see that we have a neutral molecule as long as we have 1 cation and 2 anions. Oftentimes it's not going to be as easy because different atoms are going to be giving up more electrons or less electrons than another atom can take. For example, if we want to determine the chemical formula for aluminum oxide, this is a little more tricky. Well, the name aluminum tells us that we're dealing with an aluminum atom. And oxide, the "ide" part, tells us that it is an ion, but the "ox" tells us that we're dealing with oxygen. So now we're going to look at the electron configurations to look at their valence electrons. Aluminum has 3 valence electrons. So in order to have a full octet, it could either gain 5 more or lose these 3. And that's easier, is just to lose 3 because it takes less work. So when aluminum has given away 3 electrons, it's left with aluminum 3 plus for its electrostatic charge. Oxygen has 6 valence electrons. It can either give away all 6, or it could take 2 electrons from another atom. Oxygen is going to choose to take the electrons, which leaves it with an O with a -2 charge. So the number of electrons being transferred between these atoms is uneven. Oxygen only accepts 2 electrons to fulfill the octet rule. So if aluminum was giving away 3, 1 electron would be left over. What this means is that multiple atoms of both the oxygen and the aluminum are needed. So here we have aluminum with its 3 valence electrons being given away. 2 of them can go to the oxygen atom, but there is 1 unaccounted for. So if we have a second oxygen atom, now all of aluminum's valence electrons are accounted for. However, this oxygen atom is not fulfilling its octet rule. So we have another aluminum atom. Now we have 2 oxygens that have full outer shells and they are very happy and stable. However, this aluminum has 2 more electrons that it would like to get rid of. So if we have a third aluminum, now we have a complete transfer of electrons. No electrons are left floating around freely, and all of the atoms have a full outer shell. So aluminum chloride is going to have 2 aluminum atoms. Aluminum oxide has 2 aluminum atoms and 3 oxygen atoms. And so we see that the overall charge will be negative because all of the electrons have been transferred. We can look at this mathematically also. Here we have 2 cations, each one of them has a +3 charge, for a total component positive charge of +6. We have 3 anions, each of them with a -2 charge, for a total anionic component of -6, leaving the overall compound net charge as 0. And again, here we've kind of drawn out the valence electrons and how they've been moved to the other oxygens. So our chemical formula for aluminum oxide is Al2O3. And again, this 2 is telling us that there are 2 aluminum ions. And the 3 as a subscript tells us that there are 3 oxygen ions. People often get confused and they think the 2 and the 3, or the subscripts involved in the formula, are telling us the charge of the ion, and that is not the case. It's telling us how many of each are involved. So when you are naming ionic compounds, there's a couple rules to follow. First of all, the cation's name is written first, and this is very easy because the cation keeps the same name as the element. So in aluminum oxide, the aluminum ion is still referred to as aluminum. Secondly is the anion name, and the anion keeps the root of the name, as we learned in our last unit, plus that adds the suffix "ide." So in aluminum oxide, the oxide means oxygen, and the "ide" is telling us that that oxygen is part of a compound with the aluminum oxide. Here are a few practice problems for you to work on in figuring out how many of each element are needed to figure out the formula for the compounds, and then you can also try it by doing their names. And here you can try that by using the names to figure out the compounds. And here are the answers.